Good morning, students. Today's session we are going to discuss about how we are going to identify the process for controller tuning. Okay, so in the previous session we have learned about the controller tuning rules proposed by Zagler, Nichols, and Cohen-Cohn. So once a controller tuning rules is proposed, next you have to identify. Okay, so before to design the controller, first you have to identify the process identification. Okay, so the three methods used for identifying the process. Okay, so here you can see that. One is a process reaction curve, second is a frequency response diagram, and third is a pulse response. Okay, so it is very important to study the dynamic behavior of the process, and that is called as a process identification. Okay, so only by knowing the process you can able to design the controller using a different controller setting rules. Okay, so first one is a step test. Okay, so already we have discussed in the Cohen-Cohn tuning method, we have to give a step response, a step input to a process so that you will get a process reaction curve, and in that curve you have to determine what is the respective parameter. Okay, so for many process in the chemical industries, okay, so we take a process reaction curve which is a S-shaped curve, and we have to fit that S-shaped curve in the second order dead time process model. Okay, so you know very well already you have a second order process will be represented as Kp divided by tau p tau 1 s plus 1 into tau 2 s plus 2 s plus 1, and here tau 2 s plus 1, and with the dead time you will have e power minus td into s. Okay, so this model is extension of the CC tuning method. Okay, so here you are going to use a computer simulation to fit the variety of model to the process data using the least square method. Okay, so here olden days they use a method called loop pro. Loop pro is the easiest and most efficient method. Okay, so what they have taken is collected the data. Okay, and first data point in the file must be a steady state value. Okay, and test must be done by a test to dominate the process noise. Okay, so here you can see that you take a process model, excite that with a step input and collect the response. Okay, so so you have that response. Okay, so once you get the response, then try. Okay, so similarly, we are fitting the same process output with the second order plus dead time process, and it is found that the second order model is closer to the first order. Okay, so because it is clear that it is a it is a two tank storage system. Obviously, it should fit with the second order model. Okay, so in this way, we are doing a step response model, that is A-shaped curve. We are fitting the model. Okay, coming to the next one is a pulse or double testing. Okay, so here you are going to instead of giving a step input, you are going to give a pulse input. I hope you know very well pulse is nothing but it is it is a step it is a series of step inputs. Okay, this is one pulse and this is another pulse. When you combine these two, you will get a pulse. Sorry, it is one step, another one step. So when you combine, you will get a pulse test. Okay, so here the pulse is introduced in the as a variation in the wall top pressure was done for a step testing. Okay, so once the open loop system is allowed to reach the steady state response, steady state, after which the wall top pressure is displayed from the steady state for a short time, then return to the original value. Okay, so here the pulse is a rectangular shape in a experimental. Okay, so in some cases we will go for a double testing also. Okay, so here you can see that instead of giving a single pulse, you are going to give a double pulse. Okay, so here we are skipping. Okay, so you might see that input to the process is 50 60 40. Okay, and 40 then back to 50. Okay, so 40 to 50, this is equivalent to a two pulse test having 50 60 40 50. Okay, so instead of having 50 60 40 50, here you can replace that by a 50 60 50. Okay, and another one we can have 50 40 50. Okay, so here you can see that perform back. Okay, so this is called double pulse testing, where it is similar to a a shaped curve. Okay, so here you are identifying the process using this respective double pulse testing. Okay, and coming to the next one is frequency testing. Okay, so frequency testing, as already discussed, we are going to give a sine wave as input in a frequency testing, where you are going to compute the magnitude and phase plot. Okay, so for the same chemical process, you are going to undergo a frequency testing. Okay, so here you are going to give a sine wave as an input, and you are going to collect the respective output. Okay. Mm, and try to fit that with the first order plus dead time process as given by the loop pro design tool. Okay, so here to preserve the sinusoidal signal in the flow of manipulated variable, the valve must be a linear valve. Okay, so in 1960 the frequency response method was first introduced to the chemical engineer as a means for process identification. Several chemical and petroleum companies constructed the mobile units containing a low frequency sine wave generator and recorder, and could be moved to a processing unit in the plant for the purpose of frequency testing. Okay, so but the frequency testing, it takes long time to collect its respective response. That is a drawback. Okay, but it is more accurate and provides a satisfactory process identification. Thank you, students.